this example, we want to determine the amplitudes of motion of the three masses in figure when a harmonic force Ft, which is equal to F naught sine omega t, is applied to the lower left mass with m is equal to 1 kilogram, is equal to 1000 Newton per meter. If not, the amplitude of the external force is 5 Newton. And the frequency of the excitation is 10 radian per second. We want to use the mode superposition method. So similar to the previous examples, we need to extract the free vibration equation, solve the equations. Of course, here, because the external force is harmonic, we can easily solve it by considering a harmonic response. So we can extract the equation of motion. Here I wrote the final equation of motion, but in the exam, you should consider that you should derive the equation of motion. I mean the procedure. For example, if you are using the Newton's second law, you should write the force equation or moment equation to extract the governing equation. Or if you are using the Lagrange equation, again you should write the kinetic and potential energy equations, and find the derivatives and extract the governing equation, because the procedure to extract the equation of motion usually has 20 to 30% of your mark. So if you want to get a good mark, you need to write the procedure to extract the governing equations, and in fact in this way I can help you to increase your mark, because extracting the equation of motion is easy and usually you can get a good mark from this part. So in the exam, please write the procedure. I mean, if you write the final equation of motion like this and you do not mention how to extract these equations, you will lose the mark of this part, and this mark is usually 20 to 30% of your total mark. So to extract the equation of motion, for example, for this problem, if you want to use the Newton's second law, you can plot the free body diagram for each mass separately. For example, for the mass 2m, you can plot the free body diagram. We have the mass 2m. We consider the degree of freedom. For example, this one is defined x1. For this one, we define this x2. And this one, we define the mass x3. So you need to define the coordinates, generalized coordinates that you are using. We have the mass 2m. This mass, when it going down in the direction of x1, we will have one force due to the spring in the left, and it's equal to k times by x1 minus x3. We have another force here due to this spring, the right spring, and it's equal to k times by x1 minus, sorry, this one is x2, I made a mistake, x1 minus x2. We have one force due to the spring in up, and this one, and it's equal to k times by x1. Here in this free body diagram, we neglect the weight because create some initial deflection. It must be equal to 2m with the acceleration x1 double dot. So we can write the force equation for this mass. It will be 2m x1 double dot is equal to minus k x1 minus k times by x1 minus x3, and finally minus k times by x1 minus x2. So if you simplify, you can extract the first equation. The first equation is the first row of this matrix, 2 times by x1 double dot. The x2 double dot and x3 double dot will not appear in this equation. We have 3 times by x1. As you can see, if you move them, we will have kx1, kx1, and again another kx1. So it will be 3 times by k times by x1. K is equal to 1000, so it will be 3 times by, here we have 1000 multiplied by x1. Here we have minus k times by minus x3, so it will be plus kx3. When you move it to the right hand side of the equation, it will be minus k times by x3, or minus 1 times by x2 and x3. As you can see here, again for x2 we have the same k times by x2. When you move it to the left side of the equation, it will be minus k times by x2. So this is the first equation. The second equation can be obtained from the free body diagram for the second mass. For the second mass, we only have the force due to the spring, this spring, which is k times by x2 minus x1. And again, this, in this free body diagram, we neglect the weight. It must be equal to the mass m with acceleration x2 double dot. Again, if you write the force equation, you can extract the second equation, which is this equation. And you can see there is no non-homogeneous term in this equation. It's equal to 0. We will have minus k times by x2 minus x1. It's equal to m times by x2 double dot. Okay, so when you move it to the right hand side of the equation, it will be mx2 double dot plus kx2 minus kx1 is equal to 0, which is the second equation. And finally, for the last one, this mass m, if you plot the free body diagram, we will have a force for this spring k x3 minus x1, and also we have the force F. Again, it must be equal to the mass m with acceleration x3 double dot. So you can write the force equation for this mass. We will have minus k x3 minus x1 plus F is equal to mx3 double dot. And again, if you move this term to the right side of the equation, it will be mx3 double dot plus k x3 minus k x1 is equal to F, and F is F naught sine omega t. So as I told you, you should write all of these calculations in the final exam. If I ask you to write the response of a system, you need to explain how to extract these governing equations. And here in this example, I explained how we can extract the equation of motion using the Newton's second law. Or you can use the Lagrange method. Maybe in the exam, I ask you to use the Lagrange method. So if I ask you to use the Lagrange, you need to use the Lagrange equation. If you write the equation of motion using the Newton's second law, you will lose the mark for that part. So even if you write the correct equation of motion, but if you don't use the Lagrange equation, you will lose that marks. So you need to write the Lagrange equation to extract the equation of motion when I asked you in the problem description. So this is the equation of motion, and now we want to obtain the amplitude of the motion for the three masses in the figure. So we need to extract the response by considering the free vibration analysis, we can obtain the frequencies and mode shapes. Here we have the matrix K, which is the coefficient of vector X, and matrix M, which is the coefficient of the acceleration vector. So we form K minus M omega squared multiplied by x1, x2, and x3, which are the amplitude of the response. We assume that the response is xt, the vector x t is equal to the vector of uppercase x, or the amplitude, which the vector of uppercase x in fact is this vector, multiplied by, for example, sine omega t. And once you substitute this response in the equation, you can extract this relation. So we will have this matrix, the matrix of coefficient. The determinant of this matrix must be equal to 0 for a non-trivial solution. So we need to calculate the determinant of this matrix. To calculate the determinant, you know, the determinant of this matrix is equal to this component multiplied by the determinant of this matrix. This component multiplied by the determinant of a matrix, which its first column is these two components and the second column is these two components. Of course, we have one negative sign, and finally this component multiplied by the matrix of the determinant of this matrix. So we can write it here. I wrote the how to calculate the determinant. It must be equal to 0. And then you can simplify and substitute omega squared is equal to alpha, similar to the system with 2 degrees of freedom. But in the 2 degrees of freedom systems, you can extract an algebraic equation from order 2. But here, when you substitute omega squared is alpha, you will extract an algebraic equation from order 3 in terms of alpha. Then you can use the different methods to solve this algebraic equation and obtain the roots and determine the natural frequencies. The first natural frequency, omega 1, is 14.82. So by using this omega 1, you can substitute into the equation. I mean, here, when you obtain omega 1, you need to substitute omega 1 is equal, omega is equal to omega 1 in this equation and in this one as well, and in the third one. And then, or here, in fact, here you should substitute omega is equal to omega 1. Then this component will be multiplied by x1, minus 1000 will be multiplied by x2, and again minus 1000 will multiply by x3. This is the first equation. The second equation, this term minus 1000 will be multiplied by x1. In this term, the second component, you should substitute omega is equal to omega 1 multiplied by the second component, or x2. Here we have 0 multiplied by x3. And from the third equation, you can obtain minus 1000 multiplied by x1 and 1000 minus omega 1 squared. Here you should substitute omega 1 squared multiplied by x3 is equal to 0. So you can find the relation between the amplitudes x1, x2, and x3. And as you can see here, I obtained that x1 is equal to 0.78 times by x2. x2 is equal to x2, and x3 is obtained that is equal to x2. So this is the first mode shape. For the second mode shape, when you substitute omega is equal to omega 2, you can extract that x1 is 0, x2 is x2, and x3 is equal to minus x2. And finally, for the last one, when you substitute omega is equal to omega 3, you can extract the third mode shape. When you substitute, you can extract that x1 is equal to minus 1.28 times by x2. x2 is equal to x2, and finally x3 is equal to x2. This relation can be obtained from the equations in the previous slide when you substitute omega is equal to omega 1 to omega 3 respectively. Okay, so these are the mode shapes, and now we need to normalize these vectors to normalize the vectors, you can multiply and calculate this equation. The first mode shape transpose multiplied by matrix M multiplied by the first mode shape, it must be equal to 1. When you calculate this, the x2, which you find all of the relations in terms of x2 can be obtained. X2 must be equal to 0.56. Here, then you can, if you back to the previous slide, when you obtain the x2, this term, for example, for the first one, we find it must be equal to 0.56. So the first component is equal to 0.78 multiplied by 0.56. The second and third component will be equal to 0.56. So the first column in the modal matrix, as you see, is equal to this vector. This is the first mode shape. When you substitute x2 is equal to 0.56. For the second column, you will do the same with the second mode shape. As you can see, x2 transpose multiplied by matrix M multiplied by x2, it must be equal to 1. So from this equation, you can obtain that x2 for the second mode shape is 0.71, and you can extract the second column. And finally, the last column, which is obtained from the third mode shape, you can substitute into this equation x3 or the third mode shape transpose multiplied by matrix M multiplied by the third mode shape, it must be equal to 1. And from this equation, you can obtain that x2 in the third mode shape is equal to 0.43. To calculate this matrix calculation, we have one vector. Let me show you first. Back to the previous slide. To calculate this matrix, we have one matrix M. This is the matrix M. For example, when we have let's do for the second mode shape because it's easier to write. The second mode shape is 0, 1, minus 1 multiplied by x2. So if you want to calculate this, here we have matrix M. So the mode shape transpose is a vector array which is 0, 1, and minus 1. This is the mode shape transpose. Of course, we have one x2. I will write it at the end. We have vector the matrix mass 2, 0, 0, 0, 1, 0, 0, 0, and 1. And it must be multiplied by 0, 1, and minus 1, which is the second mode shape. I'm writing the equation to normalize the second mode shape, and also we have x2 squared. Okay, so we need to calculate this matrix. I mean, it is equal to 0, 1, minus 1 multiplied by a vector. The first component is this row multiplied by this vector is equal to 2 times by 0, 0 times by 0, and again 0 times by 0 is times by minus 1. So the first component is 0. The second component is 0 multiplied by 0, 1 multiplied by 1, plus 0 multiplied by minus 1. So it will be 1. And finally, the last one is 0 multiplied by 0, 0 multiplied by 1, and 1 multiplied by minus 1. So this is the response of this matrix multiplied by this vector. And again, we have x2 squared. And now we will have 0 multiplied by 0. Let me change the color. 1 multiplied by 1 and minus 1 multiplied by minus 1. So it's equal to 0 multiplied by 0 is 0 plus 1 multiplied by 1, which is 1, and plus minus 1 multiplied by minus 1, and it's equal to gain 1, and finally multiply by x2 squared, it must be equal to 1, and from here you can conclude that x2 squared is equal to 1 divided by 2, and from here we can conclude that x2 is equal to a square root of 1 divided by 2, or 1 over square root of 2. So this is the x2, and then we can substitute. So this is the procedure that we use. The initial mode shapes are obtained from the natural frequencies, as I told you. Here, when you obtain the frequencies, when you obtain the natural frequencies in here from the equation of the frequency, by using this equation, when you solve this equation, you can obtain three roots, omega 1 to omega 3. In this equation, when you substitute omega is equal to omega 1, you can extract their first mode shapes, as I told you. For example, in the second equation, here when you substitute omega is equal to omega 1, you will have minus 1000 multiplied by x1 plus 1000 minus omega squared multiplied by x2, and finally 0 multiplied by x3, it must be equal to 0. From here you can find that x1 is equal to 1000 minus omega squared divided by 1000 times by x2. So here, if you substitute omega is equal to omega 1, you can find the first relation between x1 and x2 for the first mode shape. Here, if you look at, if we go to, let me close this, if you go to this equation, here, you can see this relation x1, the first mode shape. We find that x1 is equal to 0.78 times by x2. In fact, when you substitute in this equation omega is equal to omega 1, you can conclude that x1 is equal to 78 times by x2, and x2 which is equal to x2, but the x3 can be obtained from the other equation here. From the third equation, you can obtain the relation between x3 and x2, or from the first equation. So you have three equations with three unknowns, but because this omega 1 is your eigenvalue, when you substitute, you can obtain only the relation between x1, x2, and x3, similar to the system with 2 degrees of freedoms. Here we can find a relation between x1, x2, and x3. In this example, I wrote a relation between x1 and x2 and x3 and x2. So in fact, I wrote the response as a function of x2. So this is the first mode shape. For the second mode shape, you should substitute omega is equal to omega 2. And for the third one, you should substitute omega is equal to omega 3, which omega 1 to omega 3 can be obtained from this equation. Yeah? And once you obtain the mode shapes, you can substitute into this equation to obtain the amplitudes. Okay. You're welcome. So we obtain the modal matrix. This is the modal matrix, matrix X. And now we can use this modal matrix to find the response by using the modal analysis method. So for this purpose, we can find the QT, which is the non-homogeneous term, and it's equal to the modal matrix transpose multiplied by FT, which FT was, if you're back to the previous slide, was equal to 0, 0, and here was F naught sine omega t. So you need to calculate this matrix. I mean the transpose of this matrix multiplied by this vector will give you the vector q, and the first component of q is the non-homogeneous term for your first equation. The second component in the vector q is the non-homogeneous term for the q2, and finally the last one is q3. The third component is the non-homogeneous term for the third equation. You will have three equations: omega 1, omega 2, and omega 3 are calculated in the previous slide. You can substitute. You will have three equations with three unknowns, q1 to q3, and we can solve these three equations easily. For example, for the first equation, you will have a non-homogeneous term. You can obtain q1, which is equal to q1h, which is the homogeneous response, plus q1p, which is the particular response. The homogeneous response can be obtained from the characteristic equations. If you solve the characteristic equations, alpha 1 and alpha 2 are equal to plus minus omega 1 I. So you can find the response for the Q1H, or the homogeneous response, which is C1 sine omega 1t plus C2 sine cosine omega 1t. And for the particular response, according to the form of Q1, you can consider the response, because Q1 definitely will be a combination of harmonics with frequency omega t. And then you can consider that, for example, q1p is equal to a times by sine omega t, which this omega is the frequency of the excitation, the frequency of this q1, plus b times by, for example, cosine omega t. And then you can substitute into the equation, into this equation, to obtain a and b, similar to the single degree of freedom systems. So we will have three equations which are uncoupled, and you can solve them directly and obtain the response. Okay, any questions so far? Is it clear? No questions? Okay. Okay, in the next example, we want to use the Lagrange equations to derive the equation of motion for this system. Here we have a system with how many degree of freedom do we have here? Can you tell me? We have a pulley which is connected to a spring, so it can move. The mass center of this pulley can move with a degree of freedom x1. We have a mass 3m which is rotating about this around this pulley, and we define a new degree of freedom x2 for this mass. We have another mass m here, which again is moving in vertical direction with a degree of freedom x3. And also this pulley, at the same time, when it's going down, it can rotate about its center with angle theta. So the degree of freedom for this system is 1, 2, 3, and 4. So we deal with a system with 4 degree of freedoms. We want to use the Lagrange equation to extract the equation of motion for this system. Also, you can use the Newton's second law, but in the exam, if I ask you to obtain the equation of motion using the Lagrange equation, you must use the Lagrange equations, and you cannot obtain the equation of motion using the Newton's second law. So for this purpose, we need to write the kinetic energy and potential energy. Here we have one mass 3m. The velocity of this mass, according to the degree of freedom x2, is x2 dot. So the kinetic energy for this mass is half times by 3m times by x2 dot. This is, we have another mass here with degree of freedom x3, so it will have a velocity of x3 dot. So the kinetic energy is half times by m times by x3 dot, which is here, this term. And finally, we have a pulley, this pulley with mass m, uppercase M, and the mass moment of inertia J naught. This pulley is a rigid body. Its kinetic energy includes two parts. The first part is due to the translational motion, which is obtained with the degree of freedom x1. So it will be half times by m times by x1 dot squared, this term. And the other part of the kinetic energy is due to the rotation about its center with the degree of freedom theta, and it's equal to half times by J naught times by theta dot squared. So this is the kinetic energy. We have the potential energy. One due to this spring is equal to half times by k times by x squared, because the edge of the spring is moving by x1, this degree of freedom. So it will be half k x1 squared. We have another spring here with the stiffness 3k. It's moving with the degree of freedom x3, so it's equal to half 3k x3 squared, this term. And finally, we have another spring here, which one edge, this edge is moving with x3 in downward direction, and in fact this degree of freedom will pull the spring. Here this edge is moving with two different degree of freedom. One due to the x1, this point will go down, and in fact the x1 will push the spring. But we have another degree of freedom because this point at the same time is located on the pulley and is rotating in clockwise direction due to the theta, as you can see, and it's equal to r theta. Due to this rotation, this spring will be pulled, so we will have two pull and one push. We can consider one of them will negative and the other one can be positive. Here I assume that the degree of freedom which pull the spring are positive, so x3 which is pulling the spring is positive, r theta which again is pulling the spring is positive, and the x1 which is pushing the spring is negative. You can change this direction. I mean, if you assume that x3 is minus, minus, and positive, you can change it. Again, the result will be the same, no different. Okay, so this is the potential energy, and as you can see, we neglect the weights because these forces, these masses are create some initial deflection in the springs, so we can neglect the weight in the potential energy. And finally, the work done by the external force, we have F1, F2, and F3. We have three external force. F3 is applied to the degree of freedom x3, so the work done by this force is F3 times by x3. The F1 is applied to this point, so the degree of freedom of this point in translational motion is x1, so the work done by F1 is F1 multiplied by x1. And finally, for the F2, we have the same, F2 multiplied by x2. These are the work done by the external forces. And now we need to substitute into the Lagrange equation. Is it clear how to extract the kinetic energy and potential energy? If there was no theta, it means that this pulley will be fixed. It means that if the pulley was fixed and it couldn't rotate, it should be mentioned in the problem description. But here you can see we have rotation. Here we have the rotation. It means that the pulley at the same time when it's going down, it has a rotational motion. If it was fixed, I mean here at this point O, it was fixed and it couldn't rotate about point O, then in the degree of freedom of the system will decrease, and instead of 4, it will be 3. And it will be x1, x2, and x3. And then you can consider this pulley as a mass as a particle. So the kinetic energy for this pulley was equal to only half times by mx1 dot squared, and this term was 0. But here we have another degree of freedom, and that's theta. So this is a system with 4 degree of freedom because of this theta, because this pulley at the same time has a rotational in addition to the translational motion. Okay. So now we need to substitute into the Lagrange equation. We will have 4 equations, as I told you, because this is a system with 4 degree of freedom. You should calculate the partial of t with respect to x1 dot, and then calculate the Lagrange equation with respect to x2, x3, and finally for the theta. So we will have 4 equations by substituting into this Lagrange equation. For the kinetic energy, if you substitute, we will have the partial of t with respect to x1 dot, the partial of t with respect to x2 dot. So you only need to substitute and calculate some mathematical calculations. We need to calculate some derivatives with respect to x1 dot, x2 dot, x3 dot, and theta dot, and then the derivative of these terms with respect to time. So easily you can find the derivatives for the kinetic energy. The next step, you need to calculate the derivatives with respect to the potential energy. As you can see, the derivative of t with respect to x1, x2, x3, and theta are equal to 0 because the kinetic energy does not include x1, x2, x3, and theta. So these terms are all 0, but the derivative of v with respect to x1, x2, x3, and theta can be calculated. The derivative of v with respect to x1 is equal to the derivative of this term with respect to x1 because this term is 0, and here we have x1 as well, so it's equal to 2 times by half times by k times by x1, which is equal to k x1. The derivative of this term, this half will cancel out with this 2, with respect to x1 is equal to 2 times by k times by derivative of this term with respect to x1, which is equal to -1, multiplied by this term to the power of 1. So we will have minus 2k times by this term x3 plus r theta minus x1. Okay, so this is the partial v with respect to x1. The partial of v with respect to x2. Here we don't have x2, here we don't have x2, and in this term we don't have x2, so it's equal to 0. The partial of v with respect to x3, here we have x3. In this term we don't have x3, it's 0, and again here we have x3. So the derivative of this term with respect to x3 is equal to 2 times by 3 divided by 2 times by k times by x3, or 3 times by k times by x3. The derivative of this term, this half will cancel out with 2. We will have 2 times by k times by derivative of this term with respect to x3, which is equal to 1, and multiply by this term, and it's equal to 2k times by this term. And finally, the derivative of v with respect to theta. Here we don't have theta, here we don't have theta, and only in the third term we have theta, and it's equal to 2 times by k times by derivative of this term, which is equal to r. The coefficient of theta is r, multiplied by this term. So it's 2kr multiplied by the parentheses. And finally, the derivative of w with respect to x1, x2, x3, and theta. You can calculate the q1 to q4. So now we have these terms, and you can substitute into the Lagrange equation to obtain 4 equations of motion. Okay, any questions so far? Is it clear? If you don't have any question, we can wrap up this session, and this example can be solved in next week. Any questions? Okay, so we will have a 10 minutes break, and after that I will start the tutorial. The tutorial, we will solve the problems for this week and previous week, because last week we didn't have tutorial session. So today I will solve both the problems for this and last week. Okay, thank you for your attention, and after 10 minutes break